absolutely have a lot to do today. So we are, I've given you a little Skittle bag to kind of give you some sugar. So we have enough energy to get through the last hour and a half of the day. We're going to start with this problem. We are going to kind of almost finish all of normal distributions today. Almost everything that you need to be able to answer every question in a normal packet will be answered today. Okay? We're going to talk about Z-scores. We're going to talk about normal CDF on the calculator. We're going to talk about inverse norm, what it means to shade, what it means to find, how to use the empirical rule a little bit more effectively. And then we're going to finalize our kind of the end of what we're going to talk about today is how do I tell whether a data set is normal? And so I had you guys weigh in ounces your bags of Skittles, and we'll come back to, we collected some data, so we'll come back to that at the end of class today. Okay? I had you write on the board, so we're good. For now, for the warm-up, I want you to go ahead and look at this question. I want you to draw it out like you did for your homework. Your homework should have been super easy on normal curves, and the first 5 problems were just draw it, right? And then 6, 7, is it 6, 7, 8, and 9, or just 6, 7, and 8, right? The last 3 problems, not only did you have to draw, but you had to answer a question or something. It was pretty easy. I promise you to get a little harder as we go through, but it's a nice start, right? Huh? Why did I give you easy work? Oh, it's a matter of the way the questions are worded are a little bit different. It's not just draw 6 graphs. So we're going to start with this question, this problem. Okay, we're talking about birth weights of babies. I'm telling you ahead of time that they're normally distributed. So I want you to treat it like your homework. I want you to go ahead and draw 1, 2, and 3 standard deviations above and 1, 2, and 3 standard deviations below the mean and answer the 2 questions that you see. Okay? So did you get these values when you added 3 standard deviations above and subtracted 3 standard deviations, correct? So the first question says between 6.3 and 8.9, and we're looking at this particular one, so 6.3 and 8.9, well, that just happens to be the purple values, and so using our empirical rule that we used last class, what'd you get? 68%, right? Okay, that's pretty straightforward, nothing too difficult about that, looking at the numbers right on our graph. What about the second question? What happens with the second question? Are 4 and 10 numbers that you see on our graph? So they're a little different. So if I was going to estimate, I'd say 4 is about right here, right? And 10 would be about right here. So we're looking at about this part if I was going to shade, pretend like I'm shading all of this. And if I had to estimate, would you say maybe 96%, something like that? I don't know. I'm just estimating, throwing a number out there. It's a little bit more than 95 on the left, a little bit less than 95 on the right. I don't know, about 95%? I don't know. Just saying it's a number. You know it's some big number. Would you agree? All right. But we can actually find it exactly. And I'm going to show you how to do that today. Okay? So that's kind of, we're going to come back to this question. What I'd like us to talk about, and this should, okay, it should all be coming back to you now, this whole idea of a z-score, okay? And z-scores are something you should have learned in Algebra 2. You should have learned in Algebra 2. I say should have, it depends on where you came from and who you had, but it is part of the Virginia Algebra 2 curriculum. They used an X instead of a Y, and I think your textbook does too. Don't worry too much about that. But this is, in fact, the formula for a z-score. Anybody want to remind me what a z-score is? What is it? It's a number. What kind of meaning does it have? We're going to talk about that, okay? Let me give you the formula first. I always, for some reason, tend to write this as an X, not a Y. It doesn't really matter. But let me break down what the pieces of the formula are. What is the U with the tail? Nope. That's the mean, okay? That's the population mean. Sometimes we use an X bar, right? That would be the sample mean. And then what about down here? That would be your standard deviation, okay? So we talk about a z-score really is how many standard deviations away from the mean are we? Okay, that's really what a z-score is. And we're going to investigate that in a couple of minutes. Let's look at this baby situation that we did and use our idea. And was it between 4 and 10? Was that the question we couldn't answer? Okay, so let's find the z-scores that correspond to 4 and 10. So we really want to figure out the percent between 4 pounds and 10 pounds. What is the percent of babies that are born between those two birth weights? So I want you to find the z-score that corresponds to the 4 pounds and the z-score that corresponds to the 10 pounds. So let's try the 4 together. Okay? The z-score, the x value is going to be the number we're looking for. So it's 4 minus. And then the mean was what? 7.6. And the standard deviation was 1.3. Tell me what z-score that is. Do we expect it to be positive or do we expect it to be negative? We have a 7.6 mean. We're looking between 4 and 10. So we're looking for this. What'd you get? Negative 2.7. Let's 2.7 what? 2.76. Okay. Do we expect it to be negative? Remember what I defined in words what the z-score was. The z-score is how far the value is, how many standard deviations away from the mean is that value. So from the center, we went left to get to 4, right? So do we expect our z-score to be negative? It's from the left of center. We went left, so that would imply a negative, okay? What about 10? Do we expect that value to be positive or negative? Positive. Very good. So let's make sure that happens. So our z-score, so we're going to have 10 minus 7.6 divided by 1.3. And tell me what you get there. 1.836? Oh, 46. Okay. Positive value. Is that okay? Not too bad. So what I want to say, or what I want to talk about, is that this graph that we started with up here, between the 4 and the 10, we are actually going to standardize. We're going to do it on what we call a standard normal, and that would include the z-scores. So instead of a 4, we're going to do negative 2.76. Instead of the 10, we're going to write 1.846. What do you think in a standard normal, when I'm talking about z-scores, what do you think the middle value is? What's the mean? 0, right. Okay? So we can take this idea and we can actually take these two z-scores and use our calculator and find that. Now, back in the olden days, when I went to school, before we had these fancy calculators, we had tables that we used to find these answers. They still exist. They are in the back of your textbook. I'm going to try to pop one up here to show you. Here is a z-score table. That's what it looks like. Okay? You would literally find the z-score in the margin, go over, and you'd find the number. Okay? It's kind of like they used to have trig tables too back in the day, and logarithmic tables, but now you can just use a calculator. So these are really antiquated, like they're really old-fashioned. You actually are going to get some z-score tables on your exam as well. I don't know why they can't just say, we don't need them anymore because we all have calculators. Okay? So I'm not even going to really show you the tables. I'm really going to focus on the calculator. So what I need for you to do is to get your calculator. We're trying to find, we're told it's normal, so we're going to use the normal distribution. So pull up your calculator, and let's look at the normal distribution. Where do I go to find it? Second bars, good. So we're going to go there. Got some old stuff on here we need to clear out. See if I can get it to come back up. There we go. Well, that's a good question. That was what I was going to ask you. Is it going to be PDF or CDF? When it comes to normal, because it is a cumulative density function, the normal curve is, it's not discrete like that, because it's continuous, we will always use CDF, okay? It's between two values. It's greater than, it's less than. We will always use CDF, cumulative. Because I don't really know. I'll just be flat out honest with you. I've never used the normal PDF before. Good question. Sorry, I can't answer it. But we are going to use the normal CDF, okay? Now, what two values am I between? What were my z-scores? Negative 2.76 is my lower bound. Look at where we shaded. Lower just means the left side. Upper will mean the right side of what I shaded. What's the right side of where we shaded? 1.846. Oh gosh, try again. Okay, negative, really, Ms. Meckert? Negative 2.76. This calculator doesn't like me. All right, and then the upper is 1.846. Good. Notice when it asked you for mean and standard deviation. The default is 0 for your mean. Since we're dealing with z-scores, standardized scores, we are looking at a mean of 0. And look at what you see for the standard deviation. It's 1. Okay? So that's the default. When you're talking about z-scores, those are the numbers you're going to use. We'll come down here, we'll paste, and we get about 96%. Isn't that about what we estimated anyway? Looking at the empirical rule, right? About 96%. So 0.9647. Okay, I agree with that. So we're going to say, and this is what I'd like for you to do. Anytime that you're asked to solve one of these problems, the AP, the College Board, really wants you to show work for z-scores if they're necessary. Draw and shade the graph. That's really an important piece. And then tell me what you typed in. They didn't used to like this, they called it calculator speak, because they really wanted you to use the tables. They're coming along, okay? So as long as you've shaded and shown the graph, put the mean on the graph. The normal CDF is going to be the lower bound, the upper bound, the mean, and the standard deviation. Okay, and what do we get? I'm sorry, 0.9647? Is that right? Okay. So that would be enough. Okay so far? I want us to look at some more problems when we're talking about z-scores. Okay, I think we'll just do the first 3. We're not going to do them all. Why can't I see what I'm doing here? No, no. There. No. It's always awesome. Did something get deleted? It did. Oh, God. Is it even recording anymore? Let's see. Okay, that's fine. So I just wanted to be able to do this. I want to do the first 3. Okay? So I want you to draw a sketch of all 3 of these. I'm giving you the z-scores this time, so you don't have to find the z-scores, which is fine. But I want you to sketch it, and then I want you to shade where it's asking you to shade, and then use your calculator to answer the question. So take a minute to sketch them, shade them, and then see what we can get because of the negative sign. So when I graph this, I'm always, since I'm talking about z-scores, I will put 0 as my center, okay? Because with z-scores, that is the mean. Negative 1.46 is to the left of that, so I will put that number here. And because the question says below, I'm going to shade below. Any questions about the picture? So what becomes the issue? When I do my normal CDF, because I'm trying to find the percent of the graph that's shaded, right? So I'm using my normal CDF function. What's the issue? You have an upper. The right-hand side is negative 1.46. And we have 0 and 1. Would you agree? What's the lower bound? Matt? Okay, so yes, you could do that. It's really some number far off to the left. Would you agree? Some number. I mean, with Z-scores, what number would be really far to the left? Negative 10? Wouldn't that be a number way off to the left? Negative 100, negative 76, negative 3,000,002. I don't care what number you use. What Matt's suggesting is that you can go ahead and put it's negative 1 times 10 to the 99th power. I'm sorry, that's not true. It's 1 times 10 to the negative 99th power. The calculator notation for that is negative E99, some really small number. That means 0.0000, I could count 99 zeros, 1. No, when you're looking here, the left-hand side is my lower bound and the right-hand side is my upper bound of what's shaded. Because negative 1.6 is the right-hand part of the shaded, even though it's negative, it's still the right-hand part of the shaded region. Okay? It's a very good question. So how do I type that into my calculator? So we're going to go to second vars, normal CDF. Where is negative E99? That means negative, some really negative number. Negative. And then E, I believe, is second the comma. And then we'll just, no. Try it again. Negative. There. This thing doesn't want to deal with me. Negative. Oh, that's because I'm pressing the wrong button. Duh. Thank you, Angelica. Negative, second, comma. E, 99. 9. There we go. The right-hand side was negative 1.46. Again, our mean is still 0. We're dealing with Z-scores. And our standard deviation is 1. So we will paste. And we get 0.072. Does that make sense? That's such a small number? A little tiny part of the graph that's shaded, right? So I expect it to be a small number. Okay? So let's keep going. So I have 0.072, approximately. Okay? So let's try the next few. Shade them, and then go. So if we look at this one, we have 0.86 should be to the right. We're looking above that, and we're looking to see, okay, what's that going to be? We have to be careful when you type this in, because what's my lower bound? 0.86. That's the left-hand portion of my shaded graph, right? So 0.86 goes there. What's the right bound? Upper bound. Some big old number off to the right. You can pick 10, 50, 100, any positive large number. So positively, if we go with this E99, that just means 1 with 99 zeros. That's like a Powerball ticket or Powerball payout. Probably more than that. Not probably it is, but anyway, 0, 1. Okay? And you got 0.194. Double check me. 5. 3 to 4 decimal places, never 2. Okay? 2's too rounded. You do 2. All right, above a Z-score of negative 2.18. What's that got to look like? When you shade that, are you shading a lot of the graph or a little bit of the graph? Because so far we've done little bits of the graph. This one's actually going to be a lot. Because if you put this here and you have 0, where is negative 2.18? Over here, negative 2.18. It says above. What does above mean? To the right of it. So do I expect my number to be over 50%? Because over 50% of the graph has been shaded. So you always want to ask yourself, is my answer reasonable? Okay. What if I got a number that was greater than 1? Would that be reasonable? Why not? Because the probability has to be less than 1. And the area all under the curve is 1, so it's never going to be greater than that. All right, so our lower bound, what's our upper bound? Positive E99, or some big number off to the right, doesn't matter. Again, since we're dealing with z-scores, we'll talk about what is a really unusual big or small z-score. 0 and 1, and what'd you get for the probability? 0.9854? That sounds right. Okay? And that's what we expected. We expected it to be more than half of the graph. So we're good. Any questions so far? Up to this point, you should have, in theory, done all of this before. In theory. And it might have been a while. Might have been a couple years ago. In theory. Okay? My next question becomes, what is an unusual z-score? What makes a z-score really big? When is a z-score an outlier? 3? Where'd you come up with 3? Okay, so if you think about the definition of a z-score, the z-score is how many standard deviations away from the middle are you? And when we drew them for our homework, we went 1, 2, and 3 above, 1, 2, and 3 below, right? How much of the data is within 3 standard deviations? 99.7%. So that's almost all. So would a z-score of 4 be unusual? Because it's outside of that 99.7. What about a z-score of negative 3.6? Again, outside of 3 standard deviations, right? So that's when we talk about being unusual or big. Is when a z-score does give us an indication of how unusual a value is. If it's outside of 3 and negative 3, we consider that an unusual score. I think that question comes up in your packet, okay? So if you're asked that question, you have to find the z-score to answer it, okay? I'm giving you hints on your homework. All right, so we said unusual would be above 3 or below what? Negative 3. Good. I agree. All right. Please don't write all this down, but I just want to kind of talk through it here. The most important coming out of what I've written down here is this notation. Did I talk about this notation last class with the capital N? I think I might have. I'm not sure which class I talked to and which one I didn't. This notation, the big N stands for normal, okay? So that means normal distribution. And then it's commonly accepted in the field of statistics to just put parentheses with 2 numbers. The first number is always the mean, and the second number is the standard deviation. Remember, there's millions of normal distributions, right? There's millions of them. There's tall, skinny ones. There's short, flat ones. There's so many of them. So we have to describe it. Let's think about for a minute the birth weight question. How would I describe that again? We were told it was normal. And what was the mean? 7.6 with a standard deviation of 1.3. So that is how we would describe. If it ever says describe the distribution, that's good enough. And guess what it tells you? Shape, center, spread. Say, what? I just went there. From September. Shape, center, spread. What is that? When I ask you to describe a distribution, aren't you supposed to think shape, center, spread? What's the shape? Well, if it's normal, what's the shape? Don't say bell curve. Bell curve is not a statistical word. What is a statistical word, though? Unimodal, symmetric, mound-shaped. That describes the shape. What's the center? 7.6. What's the spread? 1.3. Done. We describe shape, center, spread. Okay? And that happens. It comes up a lot on the AP exam. So, again, just listen. Don't write. Okay? Eat a Skittle. Which ones are your favorite flavors, by the way? I like the tropical ones. I like the purple ones. Come on. The sour ones, I have sour, but they had different weights, so we couldn't use them. So they're coming later, to be determined. We'll use them later in the year. So Z-scores, why are we using them? Okay? What is a Z-score? Z-score tells us how far away from the center, how many standard deviations away it is. And really, a Z-score, or when we take any of these crazy normal distributions, tall, skinny ones, short, flat ones, and we standardize it to one standard normal curve, all we're doing is rescaling it, right? Why? And we know that the mean is now 0 and the standard deviation is now 1. When could this be useful? Well, it's useful. In a minute, we'll tell you why it's useful. We'll come back. Sorry, this is when it's useful. I forgot this slide. Do I always have to standardize? Is my question before I get to when it's useful. Think back to our original question, the warm-up. Do I have to standardize? Did I have to create Z-scores for these? Not for the first question, because we could just use the empirical rule. But for this question, do I have to standardize? The answer is actually no. Because of this. If you look at your calculator, remember what the question is saying. Between 4 and 10 with a 7.6, we're looking at shading here, right? That's the question. If you look at the calculator, and I actually go, maybe if I look at the calculator, if I fight this thing, will it? Okay, here we go. All right, if I go to the calculator and I go to normal CDF, couldn't I just type in 4, not 1, 4, 10, and then put in the mean and standard deviation? Put in the 7.6 and the, what was it, 1.3? I'm going to have bruises on my knuckles, y'all. Is that the same answer we got before? So it's not required to standardize in this particular case. I did because I wanted to show you what a Z-score was, but it's not required. When is it required? When is it useful? It's useful in this situation. So I want you to read it. I'm going to pause the recording. I want you to read this, and I want you to maybe kind of rephrase why I have to use Z-scores here. So I need someone from this table, because this table is very quiet. I need someone from this table to read the question and tell me, rephrase it for the class. Why are Z-scores important in this case? This table. It's okay. Esmeralda, any ideas? Okay. Fernando, you want to try? I want you to rephrase it. Tell me why we have to use Z-scores. How is this question different from the birth weight question? The percents really don't matter, believe it or not. That's true. That is one of the differences. I agree. Very good. With the birth weight question, didn't they both have the same mean and standard deviation? There was one, I could draw them both on one curve. Do you agree? What's different about this one? I had 2 different means and 2 different standard deviations. I have 2 completely different normal curves. Remember, there's millions of them out there, right? So I have I have Professor Scrooge that I'm in, lucky me, okay? Because me loves some chemistry. Okay? And then my friend has Wimpy, lucky him, you know, fine, whatever. You got an 87. Whatever. Okay, I got a 68 and I'm proud of it. My question is, who did better? And if I want to compare, you can't compare the 68 and the 87. They're not comparable because they have 2 means and 2 standard deviations. So what I have to do here is I have to find the Z-score for Professor Scrooge, or for me. Isn't that me? I'm the one that's in that class. And then my friend has Professor Wimpy. Let's find those Z-scores. Let's do it. How do I find the Z-score that relates to my grade? Remind me of the formula real quick, just to remember, because it's not on your formula sheet. Of course. It's x minus mu over sigma, right? That's the mean over the standard deviation. So for Scrooge, what's the x? 68.68. That's fine, because it's the percent, right? Minus, the mean for my class was? I think it's just 0.58, isn't it? Okay, so 0.58. All right, and then the standard deviation was 0.085. Okay, so what's the Z-score? I did better than the mean because, you know, I'm good. What'd I get? What's my Z-score? 1.1 something. 1.176. All right. So I am more than one standard deviation above the mean. I'm pretty proud of myself. 68 or not, I did I. What about my friend who's bragging in my face and it's really irritating me with her little 87%? I'm not going to get physical because that is not appropriate. What I'm going to do is I'm going to mathematically show her. Okay? You think you got an 87? Well, let's actually really compare, darling. Okay? So, so 0.87 is my friend's score. The mean of that test was an 82, and the standard deviation of that class was 0.062. There's no need to mince words or to fight. I'm going to prove to you I did better. What's your Z-score? Show off. Point what? 0.806. You didn't even do better than one standard deviation of class. Ha! Oh my.
I mean, your grades don't show that.
If we were to curve the scores, you ever hear that word? The teacher's going to curve the scores. I'm going to apply a bell curve to the scores. Okay, you think that's good? Not always. Because that's what's going to happen to that 87. It ain't going to be one anymore. It's going to be lower than that. Okay? So that's, just be careful. And so that doesn't happen in high school so much, but in college, sometimes your teachers will apply a bell curve to scores, and you don't want that to happen unless you're really good or really bad. Actually, if you're really good, you don't want it because it brings you down. But if you're really bad, it's not so bad. Anyway, so who did better?
You did.
Yeah, brilliant. Okay, so I win. Okay, I mathematically proved that, I'm better. Are you criticizing my handwriting? Thank you. It's all right. All right, so we have a couple more things to do. So far we talked about what a Z-score is. We've defined it. We've talked about when it's important to use it because we have to compare distributions. We've talked about using the calculator function, normal CDF. And all of those things I'm told it's normal, and I'm trying to find the percent, right? What percent is between blah, blah, blah? What percent is above? What's the likelihood of this happening? Read this. By the way, I'm deleting this. You don't need all this information. I'll just go and delete it. Read this for just a minute. So I agree. One of the differences between the questions that we've done up to this point and this one is I gave you a picture. Okay, in this question, whereas before I asked you to draw your own. Definitely a difference. Cameron got a different one?
They tell you to write the original data set rather than the Z-score.
Well, it's asking for a Z-score, right? It says what Z-score represents. It gives you the percent. Up to this point, haven't we been trying to find the percent? Right? So up to this point, we've been trying to find it. When you're finding the percent, you use the normal CDF function of the calculator. This time, we're given it. Well, sort of. Kind of hard to read. But even if I didn't graph it, doesn't the first quartile, what percent corresponds to that? Think back to September, quartiles, uh-oh, worlds are colliding, 25%. So this shaded region was 0.25. If I said third quartile, what percent would I say? 0.75. So we are remembering things. That's good. Got a midterm coming up. Got to remember these things. Shapes under spread, quartiles. I'm trying to interject words from the past just to kind of help us. It's all anyway, so if I'm given the percent, it's a different fixed function. I'm trying to figure out what this z-score is, right? The function you're going to use on the calculator is called inverse norm. Okay? So I want you to look on your calculator under distributions and find it. When you are given the percent, you use inverse norm. When you're trying to find the percent, you use normal CDF. So inverse norm. Did you find it? Oh my gosh, this thing. All right, so distributions, inverse norm is the third function down. And it's asking, it doesn't say percent, but it says area. Yeah, that's the same thing as the percent, okay? The area under the curve is the percent. So you're going to write, you need to put it in as 0.9, I'm sorry, not 0.9, 0.25. Okay, that is the same thing as area. What about my mean and standard deviation? Are they okay to leave them the way they are? Why? Not because it's normal, because it's standardized. I'm looking for a z-score, okay? That's why. So I go ahead and I paste it the way it is, and I get this number, negative 6.45. So 0.2501, and I get this number. Did I expect it to be a negative z-score? Why negative? Because it's below 0. Okay, so I did expect that z-score to be negative. Okay. So again, when you're finding the percent, what function do you use? CDF. Normal CDF. And when I am looking for a z-score, or if I've given the percent, I am inverse norm. Good. So let's try these. Okay. Did you guys know that for those of you who took the PSAT, that those scores were released last week? Log in, get a College Board account, you can find your PSAT scores. Okay? So here's an example of SAT scores. We're just talking about math scores right now. They are actually standardized. SAT scores are. Okay? They're normally distributed. And here's in a particular county, we're not saying Prince William County, but we're saying somewhere, the mean would be 420, and the standard deviation would be 80. I'd like for you to answer some of these questions. So draw the picture for each one of these. Let's do the first one together. 420. 20% of the students scored below what value? That's another way of saying the 20th percentile. So we expect that number to be pretty small. Greater than 420 or less than 420? Less, right? So some number, I don't know what it is, we want to be less than this. Would you agree with that? And we really know that this percent here is going to be 0.2 because it's the 20th percentile. 20% scored below what value? I'm given the percent, so what function am I using? Inverse norm. What is the area I plug in? 0.2. I'm not going to use 0, 1, 1 here because I don't want a z-score. I want to know the SAT score, by golly. Right? That was pretty disrespectful there. So what numbers do I put in for the mean and standard deviation? 420, I want the actual SAT score, so I'm going to put the actual mean and standard deviation in. That's okay, you can do that. You don't always have to use 0 and 1. We use 0 and 1 when I'm looking for a z-score, that's all. So what is z-score? What do I get? Did y'all score better than that on the math portion of your SAT? 460? It's above the mean here, right? All right, try the next two. What's the 95th percentile? And then what's the middle 50%? Above 420, I agree. So we have 420. We don't know what this score is, but we know that 95th percentile would be something like this. So we know that that would make this the 0.95 in here. We're given the percent, so we're going to say inverse norm, 0.95. Are we looking for a z-score or an actual score? An actual test score, so we'll put in the actual information. And what'd you get? 5 something, right? 5 what? Thank you. 551.59. Did y'all do above that in your math score? Y'all want to know what my math score was in my SAT? No one cares. My English was not that great. My verbal was really poor. My math was 760. I was pretty good at math. Go figure, I'm a math teacher. But my verbal was not that. Let's just say that I had to take freshman English at Virginia Tech. None of my friends did. It's okay. Anyway, the last question's a little bit harder. Why? To me, I think the way that this is worded is different. Matt? Oh my gosh, you're so smart. Yes. We're not going to use 50 at all, even though that's the percentage that's given to me. Because if I have 420 in here and I'm trying to figure out what these two scores are, I don't know what they are. I'm finding them. But what I do know is that this middle 50%, right in here, this is 50%. That's what I do know. Right? Where did 2.5 come from? You're right. Or 0.25. This is 25% right here, isn't it? So doesn't this score correspond to that? And then we'll have to do this score. The right-hand score is 75%. Okay? So we're going to find two. So we'll start with the left-hand side. The left-hand side, we'll go ahead and highlight it blue, because that's what we're going to be finding here, just a color coordinate. Inverse norm 0.25. We're finding the scores here, not z-scores, but the actual test scores. And so you should get a number, something less than 420. 366, I do expect it to be bigger than the one we did up here, so that's fine. So 366.04. So that'll be down here. And then we're going to go ahead and find the right-hand side. And we're going to do the same thing. We're going to say, okay, inverse norm. But this time, Matt says we're going to use 75%, 0.75. Because if I add up all the percents to the left of the pink, that's 75%. And I still am having the same mean and the same standard deviation. What number is that? 473 point something, 96. All right. I feel comfortable. So important things to remember, okay, is When do I use normal CDF? When I'm trying to find what? Aaron, when do I use normal CDF? When I'm trying to find the percent. When I'm given the percent, what do I use? Inverse norm. Those are two distinct functions in the calculator. Know when to use what. You ready to do the Skittle? It's Skittle time. I know y'all ate them already, but we're going to actually use the data now. Are you normal, Maddie? How can we tell? Okay? You know the answer to me. I ain't normal. That's all right. How do we actually, up until this point, we have been told that the data is normal. It's been part of the problem. Given that it's normal, go from here. Now we're going to turn it around. We weighed, as you came into class today, all of these bags of Skittles. Agreed? How do I tell whether or not that data is normal? I'm going to give you a minute, and I want you to plug it into your calculator. Okay? I'm going to write it down on here somewhere. Well, go ahead and do that first. So you have all these values. These are all the weights of our Skittles bags. Why are they different from each other? If you actually look at the weight that's printed on the bag of Skittles, what does it say? 2.17. I see a lot of numbers that are bigger than 2.17. And how come they all don't? I don't think we have one that actually says 2.17. Not a single one. Liars? Let's sue. My bag of Skittles does not 2.17 grams or ounces, whatever, ounces. Why might the numbers be different? Okay, should we find the average? Maybe the average is 2.17. That's a good start. Let's actually sort them first. I know you don't need to sort them for the average, but I'm doing that because you'll need them sorted for a later reason, okay? So I'm just going to sort the data real quick. I know you don't need it for the average, but we are going to still sort it, just so we have it listed, okay? Let's find the average. What is the average? How do I find it? Stat, calc. Hello, how do I find the average? One of our stats. We don't have a frequency list this time, so make sure that you clear that out. It's just list one, okay? There's no other list we're dealing with. Stat calc, one of our stats from list one. And we're going to calculate. Did you get the same numbers I did? Okay, just make sure. If you didn't, that just means you mistyped something. Okay, so just double check. I have to write down your information because you're turning this in to me. So it doesn't matter about order for the mean. Now, I still don't see 2.17. Why do you think it's bigger than 2.17? Why is the mean bigger? I can think of two reasons. Okay. So when we weighed this, we weighed the bag too. If we had time, now that we've eaten all of our Skittles, could we have gone and weighed our bag and done some subtraction? Maybe that would be 2.17. Okay, that might be one reason. I agree. The bag weighs something. Maybe 2.17 is really just the weight of the actual Skittles. Agreed. What might be another reason? A different, totally different reason. Maybe has to do with some irregularities. But why would the average be bigger? Wrigley is the company that makes Skittles. I learned that this morning. Wrigley's like the gum, right? Why might the company Wrigley want to make sure that the average is greater than what it states on the bag? Yeah, we want to make happy customers, right? I agree. We want to make sure they're happy. We don't want some angry people. If you look at our list here, who got 2.155? Who got 2.155? Who was that weight? You did? You got robbed. You got robbed. How about 2.150? Sue them. Come on, Sam. Get angry. Your weight is less than what they put it on that bag. Okay, that's okay. So my question becomes, is this data normal? What shape does a normal distribution have? Okay, mound shape, unimodal symmetric. What we want to do is we want to use the calculator. You're going to check for 3 things, and you're going to do this on your paper. Step 1, you can go ahead and write a 1, circle it on your paper that you're turning in. Step 1 is check the shape. You're looking for it to be unimodal, symmetric, and mound shaped. The calculator can draw a sort of that. What graph, what stat plot would I go to? What stat plot would I go to see a shape? Which one of these graphs? Probably a histogram, wouldn't you say? Wouldn't a histogram show a shape? Now, I don't really like the histograms that the calculator provides because they kind of do wonky bins on the bottom. So you have to take the histogram that the calculator provides with a grain of salt, okay? So you're really looking for a relatively symmetric shape. Got it? So we're going to hit enter here. In order to see it on the calculator, you really need to zoom your screen to fit the statistics. So you're going to zoom stat. Does this look familiar or sound familiar from a couple of months ago? We're going to go to zoom. Option 9 is stat. Ooh. My block 2s came out much prettier. I think we just had too many people. This first bar throws us off. Don't you agree? We're going to say it's relatively symmetric. Probably have a smaller sample size or something. Yes, ma'am. Give me just a minute. So can we say relatively mound shape, approximately symmetric and unimodal? We're going to pretend. No. I would say mound shaped, okay? The unimodal thing bothers me because of the left. I agree, because it does have a taller peak, okay? We really do want that peak to be a little smaller, maybe cut in half. I would agree with you. Yeah. If the 2 front bars were flipped, wouldn't that be perfect? Again, the calculator creates bins the way it wants to. It's some formula. I don't know how they do it. So it's kind of wonky. So we're going to say, okay, approximately. Second thing we have to do, step 2 on the piece of paper you're going to turn in to me. All right, step 2. This one is a much better indicator from the calculator, okay? Again, if you were to hand draw a histogram, it'd be much prettier. It's the calculator that messes it up. The second graph that's going to test normality is called a normal probability plot. You should write on number 2 on the paper you're going to turn in, normal probability plot. It's a plot that's already in our calculators, and what we're looking for, now, at the histogram, we're looking for mound shape, unimodal, symmetric. With a normal probability plot, you're actually looking for linear. It graphs the x-coordinates versus the z-scores, and that's how it creates this graph. That's what the graph is. That is not so important that you know. What's important that you know is not to hurt your finger, but is this guy right here. The very, very last option on the type of stat plot is the normal probability plot. Again, it graphs the x value versus the z-score. Okay? And if we resume stat, we are looking for, in this case, we're looking for relatively linear. And it is. I could take a ruler, boom. Wouldn't you agree? The histogram didn't show it so well. I agree. But by golly, this one does. So you need to sketch on your paper, Esmeralda. Number 2, sketch the normal probability plot. And tell me, yes or no, what are we looking for? Linear. Is it linear? You should say, yes, it's linear. The normal probability plot is linear. You should have sketched the histogram in number 1. You can sketch a, pretend to sketch like a pretty one if you want. Draw a really pretty normal one. I'm okay with that. So if I'm ever asking you the question, is the data linear, you need 2 plots, a histogram and a normal probability plot. The histogram should be mound shape and symmetric, unimodal. The normal probability plot should be linear. There's yet a third thing we have to do. I'll give you a minute to write those 2 things down, though. So step 3 says we're going to draw, step 1, draw a histogram, check for unimodal symmetric. Step 2, normal probability plot. Step 3 is to compare the percentages with the empirical rule. All right. What do they mean? Well, these percentages, 68, 95, 99.7, came from the empirical rule, right? We know those numbers. So if I were going to draw a normal curve, okay, we're going to bring in this smartboard. There we go. What was the mean? What did we find it to be? 2 point something? 2.22? Can you just go to StatCalc, one of our stats for me real quick? Yeah, you're fine. 2.243, okay? 2.243. What was the standard deviation? Because I'm going to go 3 standard deviations above and 3 standard deviations below. So the mean was 2.243. What was the standard deviation? 0.066. Okay. So I need to do what I did in my homework last night. I need to add that to each one each time, 3 times, and subtract it 3 times. So 2.309. I'm going to add it again. 2.375. I'm going to add it one more time. 2.441. I also need to go back to my mean and subtract it 3 times. Is it 3 ones? This is just like last night's homework, right? What is it asking me, though? So it's saying that from here to here, 1 standard deviation above and 1 standard deviation below. Isn't that 68% of the data? Okay. So how many of these numbers are actually between 2.177 and 2.309? I want you to count them. Didn't we sort the data before? So with that's a reason why I had you sort it. 68% is between the first group. How many of them? We can count. So we're going to come up here, stat edit, and what was that first number? 2.177? Isn't this the first number that falls in that range? I want it to be bigger than 2.177, but smaller than 2.309. So I'm going to count how many of our data values is in that range. So I'm starting with this number. So I'm going to count until I get to this, to 2.309. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Uh-oh. It was just 13. Was it? I don't think that one counted. Was it just 12? Or was it 13? It was 13? Was it 13? I was just going. Was they were counting again? All right. I had to stop at 2.31, didn't I? I couldn't count that one. That goes in the next group. So let's count one more time. So 1, 2, 3, 4. Oh, God, what's a minute count? Someone count and tell me. I think it was 13. 13? Okay. So 13. And then I would keep going. The next group, so it's gonna be more than 13. Would you agree? Now we're going to the next range, between 2.11 and 2.375. We're going to count how many values are here. Between here and here is 95%. How many are in that range? So you need to do some counting. Stop for a minute, though, because I'm going to pause the recording so I can stop it for everybody else. You're going to turn this into me. If you don't finish it today, you'll turn it into me next time I see you next Thursday, okay, which is fine. Finish it. What am I comparing? What's the predicted by? So you can figure these out. These are just counts, right, in the different ranges. What does predicted by the empirical rule mean? How many values did we get? How many weights of the bags of M&Ms did we have? How many bags of Skittles, sorry. How many bags of Skittles did we weigh? How do I tell on my calculator? Try again. It's 23. Right, 23. So there's 23. The sample size was 23. How do I figure out what 68% of 23 is? What's 0.68 times 23? 15.64. They're close, right? Not as close as I would like. Close. What's the predicted for 95%? How many bags, if we knew it was exactly normal, how many bags would we expect to be between 2.11 and 2.375? Between two standard deviations. 21 point what? Where'd you get that number from? What's 95% of 23? And then what's 99.7% of 23? %68 of 23 is 15.64. 23 is a number of Skittles bags we weighed. That's all the number of values we had, okay? So we're just predicting, estimating, if you want to say it that way. 0.997 of our total number of bags is how many? 22.9, okay? So 22.9, almost all the bags, 22.9, should be within 3 standard deviations of the mean. 0.997 times 23. It's a percent of a number. So what you're going to finalize is you're going to compare these numbers. Are they close enough? They should be if it's normal, okay? Just FYI. Your homework is going to be to finish this. If you do get it done in class today, turn it into the third tray. If not, it'll be due Thursday. So will your normal probability packet, okay? The whole packet. On Tuesday, you'll be working on your midterm exam review.